All right. Good afternoon. So today we're gonna do our tutorial on deep learning and Keras and Python. So the plan is to go over this a CNN classifier, which is the LaNet, and then I will explain all the stages that you need to have in order to have your final classification. And then I will try to present two RNN models, although I will not going to ask any questions about RNNs in the exam, and there's nothing to do with, you don't need to do anything with RNN in the assignment. It's just for fun, because, if you want to implement deep learning stuff, it's good to know these two things, the CNNs and the RNNs. And then after that, there's a lot of stuff that you need to study, but these are the basic things that you need to understand. Oh, okay. So now it's on. Thanks. All right. MNIST classification. So these are the versions of all the packages that I'm using. I think it doesn't need to be exactly these versions that you need to run. A little bit, more recent should be fine as well. So, this is just for you to understand what I actually used. Yes. Not really. Anaconda is just a way to simplify your life, but sometimes it doesn't. I realize that sometimes Anaconda is not the best thing to do because it's better just to install everything. But Anaconda is just a big package with lots of things. It doesn't need to be Anaconda. But, I'm requiring Python versions 3.5 just because there are some small differences between 3.5 and 2.7, so I rather have everyone on the version 3.5. And everything else here is just simple. And again, I don't need to run on the GPU. In fact, I prefer not to for the assignment because then you need to install other things, and there are more complications around it. But if you want to run your systems on the GPU and you need help, let me know. I can help with that. Okay, so I'm going to run this example on Jupyter Notebook. Everything is online. The same files that are here, they are online, from my uni, and then you can check there. I will keep switching between here and the code. Right. So the first thing that you have is just package. We're going to import all the packages that you need. Again, to run this thing, Shift Enter. So the second thing here, I will run and print all the versions that I have that I'm using here. So these are the versions that I have, and then I will import these packages from Keras. So let's go here. All right. So Keras is something that helps you run on top of TensorFlow. So TensorFlow is the main library, one of the main libraries for deep learning programming. But running directly with TensorFlow is a bit complicated. It's not very friendly, so what people did was to implement a library that can run on top of TensorFlow. So in fact, when Keras was implemented, it could run on top of TensorFlow and Theano. Theano was the other library that people use for deep learning, but Theano now is dead. So TensorFlow survived. And Keras is something just to make your life easier to program on TensorFlow. So one thing that is coming up is, and that I decided not to do it just because it's too recent, particularly for Windows programmers, is PyTorch. So PyTorch is something that's just taking over the whole field, and it will probably be the language of choice, well, not the language, the package of choice for deep learning programmers, particularly in research. But for now, let's do TensorFlow and Keras. And so Keras comes with a lot of stuff. There are many examples on the web, forums. There are Keras page that you can check. So there's lots of resources that you can use. So from Keras, we're going to be using these things here. So we will import MNIST. So MNIST is a data set containing digits, from 0 to 9. Handwritten digits, and then we want to classify these digits into 0 to 9 classes. So from Keras has several models. One of the models is called sequential. So sequential is when you define the models in sequence. Then you're going to see how we do this. It's pretty much the only model we're going to use. And then you also have layers. In this case, we're going to use 4 different types of layers. So dense. Dense layer is like your MLP with everything connected to everything. Flatten is something that will take the filtered images, several channels and make it just a long vector. Then you have convolution 2D, so this is the convolutional filter, and max pooling 2D, which will do the max pooling. So these are things that we discussed last week, and you're going to be using today when you build a CNN. All right, so far so good. Any questions? Okay, so here's the model that we're going to implement. So this was a model proposed 30 years ago by Yann LeCun. So Yann LeCun, very, very famous researcher, brilliant person. He developed a lot of stuff in deep learning, including this model. And this model was built to read mail letters. Such that you could have an automatic system that could read, zip codes, and then, just, switch where the letter should go in a switching station. And the model is very simple. So here you have an input of 32 by 32 pixels. It's quite small. And here you have a digit. Well, it's a letter, but, replace this by a digit. And so from this input, you have a convolutional layer that has 6 filters, so that's why you see the 6. And it forms 6 feature maps of size 28 by 28. So see that the input size is 32 by 32, and the second, after you are in this layer, the size becomes 28 by 28. And the reason is quite simple. You have a filter of size 5 by 5, and it's going to be 5 by 5. You have the center, and then you have +2, +2 in either direction, which means that when you cannot go to the border, right? Because if you go to the border, you're going to have a part of your filter that doesn't go anywhere, which means that your filter has to get as close to the border as possible, which means only 2 pixels from the left, 2 pixels from the top, 2 pixels from the right, 2 pixels from the bottom, which means that you're going to lose 4 pixels in your image when you have this 5 by 5 filter. And that's the 4 pixels you lose. You go from 32 to 28. So then you have here 6 filters of size 5 by 5. And then you have a max pooling 2D, which reduces this 28 by 28 to 14 by 14. So remember, max pooling, you take 2 by 2, and then you take the maximum, and then you move 2 windows next. Again, you take this 2 by 2 maximum, and then you just keep replacing every 4 pixels by 1 pixel. And then you have both sizes divided by 2. And then the second layer, the second convolutional layer, you also have 16 filters. Well, you have filters of size 5 by 5, but now you have 16 filters instead of only 6. So now you have 16, 5 by 5. And that's why you go from 14 to 10. So you again lose 4 pixels at the borders because you have a 5 by 5 filter. And then you miss these bordering pixels. And then you will do another max pooling. That's this subsampling that you have here. That reduces your 10 by 10 to 5 by 5. Again, you divide by 2 in each side, and then you have just the 16 maps of size 5 by 5. So that's what you see here. Once you are here, so remember that you're going to have 16 filters 5 by 5. So you can imagine this matrix, right, of 5 by 5 by 16. So remember that we have here this thing called flatten. So flatten here will take this 16 by 5 by 5 matrix and transform that into a very long vector. It doesn't add anything. It just takes this 16 by 5 by 5 and transform it into a long vector. And now you have a full connection. So now you're going to have 2 fully connected layers. So these are like the MLP. So it's like having an MLP sitting at the end of your network. So the first layer of your MLP has 120 nodes. The second layer has 84 nodes. And finally, you have the last layer of 10 inputs. Each input will represent a separate class. Remember that we talked about having this multi-class MLP being trained where we have kind of a binary classifier at the end for each one of the classes separately. In this case, we're not going to have that because only one of the classes have to be correct. All the others, they have to be 0. So, if you have 10 outputs, you want the output to be 0. So the 0th output will be 1. All the other outputs will be 0. So let's say you have a digit 3 at the input. So your fourth input should be 1. Everything else has to be 0. So you have to have an activation function that will take the value from the previous layer, which is called the logit, and transform that into a binary where you only have 1 in one of the nodes and everything else is 0. So let me try to so remember that before we have this kind of binary classification for each node, and then we have n separate binary classifiers. So this is what we did in one of the classes. So for this model and for any model that is called multi-class models, we're not going to do this. What we have is these nodes, which will go through an activation layer that looks like the logistic that we saw before or the ReLU that we saw before, but now it takes these 10 inputs, and the name of this layer is called softmax. And the only thing that it does, it takes these values here. These values can, these things here can have any value. It's just the real numbers. So, what you have here is real numbers in size 10. So you have 10 real numbers. And it will transform that into binary values of size 10, but only one can be active. So only one of these guys can be 1, everything else has to be 0. So that's the softmax activation layer. So the function that is applied here is this. So let's say this layer here produces a value A. So this is the vector A that has size 10. And the output here will be, let's call the, let's say you have here x as input. So it will be an f of x, considering just this input. So let's call this guy P. I think it's going to be easier. So if you have P here, so you want to transform A into P, where A is just a real number. These are your logits. And big values means that they have bigger chances to become 1. Small values means that they have little chance to become 1, but they have to be relative to each other. And P here will be your kind of probability output, because the sum of all these values will be 1, and only one can be 1, or close to 1. And in order to transform these two, what you have is Pj equals e to the aj divided by the sum, and then you go from 1 to 10 of, e to the ac. All right, so this is the softmax function. All it does is to take the values from here and transform into 1, 0. So for example, if you have values, let's say 10, minus 10 to 1, this other side will probably be 1, sorry, not 1, so 0.99, and then 0.00001, and then 0.01, and maybe 0.001, something like this. So, most of these values will be close to 0, and only 1 will be close to 1, as long as these input values here have large differences between each other. All right, so this is the softmax activation layer, which is like logistic layer, but using all these inputs. And there's no parameter to train here. It's just a transfer function. It takes these values and transform into those values here. All right, so any questions about this? Okay. All right. So training parameters. Now we have to define all our training parameters for MNIST. I have to define this thing called batch size or mini batch size. And can someone remind me what this is? What is a mini batch size? Why do I need this? So do you remember how we train a neural net with a stochastic gradient descent? So do you remember this? Which means that we take the whole training set and divide into small sets, and then we compute the average gradient for each one of these small sets, and then compute the average over all these small sets. So a batch size is the size of these small batches that you use to compute a gradient, and that will then be averaged out. Sorry, will be averaged, with respect to the whole training set. So see, here we have a batch size of 128. So this is the size of the mini batch. This number here plays an important role in training. Even today you see papers, important papers talking about what is the correct batch size that you should use. There is no big agreement. Rule of thumb is batch size shouldn't be too big. 128 is a bit too big for nowadays standards. So usually people use 16, 32, and always multiples of 2, just to make the training of the GPU a lot faster. So, but that's what batch size is. It's just the size of this mini batches that we'll be using the stochastic gradient descent. So number of classes equals 10. So that's the number of classes that you have for MNIST. That actually could come from your data set. You don't need to specify this, just to avoid any inconsistencies. Epochs. What is an epoch? Yes, when you go over the whole training set, that's one epoch. So when you just do your stochastic gradient descent over the whole training set, that's one epoch. So 3 epochs means that you're going to do this stochastic gradient descent 3 times over the training set. So you take a mini batch, you have a gradient descent, a second mini batch, second gradient, and then you do that, take the average, and then you move towards the average. Sorry, not towards the average. Sorry, let me rephrase that. So you have the parameters of your net. You take a mini batch, you compute the gradient, and then you apply the gradient to this parameter, and then you go to the second batch, and then you we apply the second gradient, and then you do that over the whole training set. Once you are done with the whole training set, that's one epoch. And then the more epochs, the better usually is your convergence. But if you have too many of these epochs, you can overfit your training set. So you will have to find a balance between number of epochs and generalization, right? So generalization is performance on your test set in comparison to the performance of your training set. So here is number of rows and columns of your images, of your input images. And then, Keras comes with lots of things, including, to load, methods to load a lot of different training sets or training and test sets. In this case, for MNIST, there are a method that can load the whole training set for you, so you don't have to download that from the web and so on and so forth. So this is important. This is things from the past. We need to do this thing here just to make sure we have the right sizes in the right places, because you expect to have channels first and image size next and so on and so forth. So just this one, don't do anything. Just make sure it's there. so you don't have any inconsistencies when you train. All right. So now we have to prepare the data. So once we load the data, that goes into Xtrain and Xtest. Those will contain your training and test images. And what you do here is you divide by 255, which is the maximum number the maximum gray value that you have for this data, which means this will be, after this division here, will be a number between 0 and 1. So your image will now be just floating points of a matrix of 28 by 28. Each value will be a value between 0 and 1. And here it just shows the shapes of your training set. So let's run this thing so you understand what I'm talking about. So here is when I load the packages, decide on batch size, number of epochs. Here's loading the training. So just making sure the data is formatted correctly. And when I run this, I'm just adjusting the training and the test set. And then you see here that the shape of your training will be 60,000 by 28 by 28 by 1. So this is a tensor that has 60,000 elements. Each element has size 28 by 28 by 1. So your images are not colored because you only have one channel. Here's it's just a gray scale. And then you have sizes 28 by 28. And you can also print the shape of a test set. Test set will have 10,000 test samples. And each test sample will also have size 28 by 28 by 1. So if you do here X test shape, you're gonna see 10,000, 28, 28, 1. So just to plot some of these images, so this is how they look like. So here is probably a 5, 0, number 4, number 1, number 9, and so on, 2, 1, 3. So this is the input that you have for your model. You see it's a 28 by 28, and then you see most of the values are just close to 0. These things here in the middle will be close to 1. That's pretty much that. There's nothing big here. Okay. Any questions so far? All right. So one thing that you need to do is, because the labels, Y-test and Y-train, they come with just a value between 0 and 9, you have to transform that into categorical. So categorical means that you will take the number between 0 and 9 and transform that into a vector of 10 dimensions, where one of them will be 1, everything else will be 0. So if you have a label, let's say Y label equals 0, you will have a 10-dimensional binary vector where the 0th value will be 1, everything else is 0. So if you have a label Y equals 3, the third one will be 1, everything else will be 0. So you need that because you will train a softmax output, and the softmax output expects 10 values. So what we're going to do is compare these labels that have 10 dimensions, binary, to the output of the network that also has 10 values, which is close to binary. They are not binary, but they are close enough. And then we just compare if they are close to each other. When they're not close, you should have a high loss. When they're close, you should have a low loss. So it's like the mean square error, but we're going to show a different error that we're going to be using for this type of problem. Okay, so then you do this for both of Y-train and Y-test. And so let me go back here. Yeah, so this is just two examples. So if you didn't understand what I said, it should be clear from here. So if you have a label 4, this is how your Y-train and Y-test will look like. It's going to be a 10-dimensional binary value. And if you have a value 9, this is also the value between 0 and 1s with 10 dimensions. All right. Okay, so what we have is a label Y that has values between 0 and 1 to 10,
And your network will output a value, let's say P, and that P also has values between 0, 1 to 10. Actually, because this is just binary, you only have a set. While here you have a range, right? So it's this is the difference. So this is the output, this is the label. So we talked about the mean square error before, which in this case we could have an error that goes through your whole training set and then basically compare these values, yi minus yi. That's your mean square error, which could work. It should work actually. And if you remember, the error here and the L2, they look like this, right? So once the error gets close to 0, then this norm here, the norm gets close to 0. But once you start increasing the error, this value here inside, either way, either direction, then the error will just grow very quickly. This thing here doesn't matter because we have to stop at 1. Both values, they stop at 1 because of the softmax. So they have to stop around that. So this should be your error, and it should work, really. You could have your mean square error to train your model, but usually that's not what you see. What you see is this thing called cross entropy loss. Instead of the mean square error or the L2 loss, what you see is the cross entropy loss when you have classification problems. So the cross entropy loss is a bit different. So what you have is, again, the sum of all your points, but then you also go through the classes. So from C equals 1 to C, and then, so let's call this comma C. So this is the Cth element of your label Y. Remember that Y has 10 elements times the log of the Pi C. So again, this is the Cth element of the value of the output Pi. Okay, I mean, pretty much you need to kind of memorize this loss function. This is the loss function almost everyone uses when they're doing classification. And the reason is that it works better for classification. That's the only reason. So if you compare the loss that you have with mean square with the loss that you have here, the difference is like this. So you have here the P, let's say here you have a log loss when, let's say, label equals 0. So just for the zeros label, so C equals 0. So when P equals to 0, which means that the zeroth element is 1, then you have 0 loss. But when it moves away from 0, it starts to increase, but it very slowly, not too far. Not a dramatic growth. But when it gets closer and closer to the wrong, that means instead of classifying this zeroth input as 0, you're classifying something else, then the loss becomes quick, very high, very quickly, a lot higher than this one. Which means that, the system basically hates to be wrong, but it doesn't care. After a point, like, 0.5, it doesn't really care. The gradient is very small, but as it becomes wrong, then the gradient is just huge, just to move to the right place. So that's the only difference between, these two losses. But you could use MSE here. It should work. But that's not what people usually do. People usually use the cross entropy loss for training classifiers. All right, any questions? You're too quiet. All right, so let's build our model in Keras. So as I said, first thing you have to tell if this model is a sequential model, which means that I will define that sequentially. So it's a model sequential, which means I will just put, step by step, each one of the layers that I want. And then it's quite simple what you do here. You add a convolutional layer of 2 dimensions. That means, just a filter of size, 2 by 2, not 2 by 2, 2 dimensions. And then you're going to have 6 filters where the kernel size is 5 by 5. So your filters will have size 5 by 5. The activation will be a ReLU. That's the activation we saw last week. And then the input shape will be equal to the input shape that I defined before, which is 28 by 28. And then you're going to have a max pooling 2D of size 2 by 2. That means my filtered images will be reduced by half. And then you add a second convolutional layer of size 5 by 5, ReLU activation, and another max pooling layer of size 2 by 2. And I'm following exactly what you see here below. And once I'm done with this, remember that I will have to flatten this layer here. So this layer, instead of being, I don't know how many maps of size 5 by 5, it will be just a big vector. So it will be vectorized. So after you do the flattening, you will add 2 dense layers. So this is exactly the MLP that we saw before. One layer with 120 nodes, the second layer with 84 nodes, both with ReLU activations. And finally, we add a dense layer with 10 nodes. In this case, the number of classes is going to be 10. And the activation is softmax. So that's the activation we saw before. And again, when you're doing classification, it makes sense to use softmax layer because, in the end, you're going to have this kind of probabilities which sum to 1 and so on and so forth. So that's why you see the softmax here. Now, the very last stage before we actually do any training, we have to compile, the whole structure. And we need to define some other things to do the final compilation of everything. One is to define the loss function. So remember that I defined the cross entropy loss, and that's what we have here. So we're going to use this loss function. So Keras comes with lots of different types of loss functions, and you can play with this. For example, you can put like a mean square error loss function and see how that goes. And then you will have to define your optimizer. So optimizers, again, Keras comes with lots of different ones, including the stochastic gradient descent, SGD. Here I decided to use this ADA delta just because it's a lot more stable. Again, up to you. You can use the one that fits better the problem that you have. And you can play around a little bit, try stochastic gradient descent, try ADA delta. And there is ADAM, there is many different types of optimizers here. So just give them a try, see how they work. But this one tends to be a little bit more stable, that's all. And metrics is just the outputs that you're going to show when you start training. So the metric that I'm going to show here is just the accuracy. It's just the classification accuracy, how often the system is correct with respect to my training and my test set. So really, this is just how often you're correct, just a percentage value. And then we do the training. So the training, you take your model that you defined and you compile, and then you have this function called fit. So the first things that you do are the training set and the label and the respective label. You have to define the mini batch size, the number of epochs, how much you want to see printing on your screen. And you also define a validation data here, which I use the X-test and Y-test. So remember, this has to do with the stuff we discussed a couple of classes ago, where you have to define your validation set. So really here, what I should have used is a validation set, not a test set, because I'm still trying to train my model, decide on things like what is the batch size I use, how many epochs I use. And for that, I have to use a validation set, not a test set. I cannot select or estimate these values using my test set. I have to use a validation set, which is part of your training set. But let's pretend this X-test and Y-test is your validation set, because I'm really just running this once. All right, so let's try to do this. So let's stop here. So I define the model, compile the model, and now the training. Oops. So maybe, I think I missed something here. Okay. Right. So when I start my training, you see here that we're going to train on 60,000 samples, validate on 10,000 samples. So this is given here. Now I'm training the first epoch, and then you see here the numbers going up, which just means the training sets that you have, and it prints out the loss, the accuracy, so these are the training loss, the training accuracy, then the validation loss, and the validation accuracy, which means that these are the results on your training and test set. I'm running this for only 3 epochs because I'm running on my CPU, not on my GPU here, so it takes a while to run. On a GPU, if you have a decent GPU, this runs just, you don't even notice. But on a CPU, it takes a long time. Yeah, so here are the 3 epochs, and then you can see the final results. So the final results are, the loss function for the training set is 0.08. So you see that the loss function comes down from 0.37 to 0.11 to 0.08. So that's what you want. So you want your loss function in the training to go down. That shows that your system is converging, your training is converging. And then the accuracy of your training should go up. In this case, 0.88 to 0.96 to 0.97. Validation should also go down, usually not as quickly as the training set, but this case it looks, this is not very common. The loss for the validation is actually smaller than the loss for the training, but you see here 0.13, 0.10, which is smaller than there, and 0.08. So that means because the validation is going down, the training is converging well, right? So it's converging and it's generalizing well. And then the validation accuracy, it starts at 0.95, so this is an unusual, very high start. And then it goes up to 0.96 to then 0.97. So I was just lucky with the initial guess that I gave for my model, so that's why you see this value so high. Then, for example, you can print the test loss and test accuracy, which should be the same as you see here, 0.08, and so on and so forth, and accuracy 0.97. And finally, this variable history, it contains all these values, and the accuracy and the loss and everything, and the training and the test. So you can actually plot them. So here you see, like if I take the history values for the training accuracy and the training and the test accuracy, I can plot them. And I can also plot the training loss and the validation loss. So if I do this, using matplotlib, then you get these results here. And I want to see this on your assignments. I want to see these graphs, which shows here, as a function of the number of epochs, how the accuracy grows, and at the same time, how the loss goes down. Again, as a function of the number of epochs. Again, the test was, probably was lucky on the initial guess of the model. That's why you see the test results so high in epoch equals 0. And that's it. So that's how you train. There isn't much more to that. So any questions?
How long until AI starts doing all that for us?
I'm sorry?
How long until AI starts doing all of that for us?
How long it took?
I was wondering how long it will take, do you reckon, for AI to start doing that programming process for us?
Oh, the programming. I don't know. I don't want to speculate. Yeah. Whatever I say will be completely wrong anyway, so I don't want to speculate. There are many things here. The training of these models, they are still kind of an art, so you need to understand what you're doing. There have been several PhD theses on how to automate this more and more. The trouble is, it's so hard to set up the whole thing that nobody does that. They just decide to do whatever they're doing, which is, essentially there are 2 ways to do the training, because you have to decide on these variables like number of epochs, mini batch size, learning rates, which I didn't discuss here, and it's hard to test these things. So there are methods to kind of estimate which are the optimal points for that. But again, it may take more time for the method to figure out that point than yourself, just to look at the results and keep trying and so on. Yeah, I can't answer that question, sorry. Okay. So hopefully, this structure is the exact structure that I expect in your assignments. Of course, with different classifiers and so on and so forth, but it's essentially the same structure, the same types of functions, same graphs and so on. It should be doable. All right, the last 10 minutes, I want to show 2 examples with RNNs. I'm not sure I have time to run this because it takes a while to run, but I will go through the whole process. So RNNs, if you remember, they are, they try to emulate several layers by, kind of repeating the same model over and over again, but with different inputs. So, if you have a text, and your text has word 1, word 2, word 3, word 4, that goes into the RNN. First, it goes through kind of an embedding, which will produce a vector that represents that word, and then it goes to your LSTM layer, and that LSTM layer receives, this hidden vector that keeps the context of your text. And here you have an output, which in the examples that I have, they can be, one is a classification output that classifies the whole text into 2 classes, or it can be the next character, which means that you can use your RNN to produce new text. So this is, these 2 things, they've been heavily used. And you will do the same, so the embedding again, then you go to the LSTM, and here you have a different value for HD, and again you have another output, and then you keep doing this over a sequence of input that can have some size S. So you go from W1 until WS, where S has to be defined, the size of your input. Okay, so you have pretty much the same thing. So you have sequential LSTM, and what I'm going to do is I will import this Internet Movie database, which has movie reviews, and then I have a classification of the movie being positive or negative. So we have good movies or bad movies based on the reviews. Then you have to define some things like the number of features, the length of your input, in this case 80. Again, the mini batch size, and then similarly to what you did with the MNIST, you load your data set with a max number of features. So max number of features here means the number of possible words that you have in your text. So the vocabulary that you can have here may have about 50,000, 100,000 different words, and when you say that I just want number of words to be 20,000, that means I just want the 20,000 words that are more frequent in your text. Everything else will be pretty much erased. And then you load that. Then you have here 25,000 training sequences, 25,000 test sequences. And then if I print the X train and Y train, which means the data input and the label for each training input, you see that a review becomes something like this. So this is just the values for your word. This is word number 1, this is word number 14, this is word 22. So you're going to have 20,000 possible values for each one of your words. And this is just a text translated into these indices. So you have to translate that because you need these numerical values at the input. And this is, each one of these will be a different review that you see. So you see that they have different sizes and so on. And here are the labels, 1 meaning positive, 0 meaning negative, good or bad reviews. You cannot work with sentences of variable length. So That's why you have this thing here, which will pad your sentences. So the sentences at this stage will have the same size. You're either going to cut to the maximum size, or you're going to pad with blank values until it fit that maximum size. So, you know, they will now have exactly the same size. So that's why you see here, all the sentences will have size 80. So you're going to have 80 words to tell if this is a positive or negative review. So the model for the RNN is a lot simpler. Again, sequential, and you add this embedding layer of size 128. So you take these words that can vary between 1 and 20,000, and then you have a layer that transforms that into a 128 dimension vector. And then you add an LSTM node that will take this input plus, you know, the hidden values for your LSTM, and then you produce an activation that is a sigmoid. So the output will be a sigmoid, just one node, and this one node will tell if the review is positive or negative. And then you compile, so the compilation will use cross entropy as the loss, so that's the loss that we saw there. And the optimizer will be Adam, metrics will be accuracy, so it outputs the accuracy. And then when you fit the X train and Y train, here only for 2 epochs, then it's kind of very similar to what we had before. We have the training score, the training accuracy, test score, and test accuracy. And these are the values that you have. So training score will be 0.8, accuracy 0.97%. And then you see that the test accuracy after 3 epochs is just 82%. So it's a lot smaller than the training. So we would need to run this more in order to have some results. That kind of makes sense. But I mean, this is kind of the structure for you to run on RNN. I'll let you play with this. And the last one, that also is available. It's pretty much the same structure, but what I'm taking is I'm taking text from Nietzsche, and I will try to build a system that can write Nietzsche's text from nothing. So this text, they look like that. So it's just a website with, you know, a large, you know, text of several things that he wrote, and you load that, and your goal is no longer to classify anything. Your goal is to predict the next character. After you've seen 40 characters, I think that's what this one means. So after you've seen 40 characters, you try to predict the next one. And then what you do is, as you predict the next one, you shift your window, and then you take those 40 characters as input, and then you predict the next one, and then you keep doing this. If you keep doing this, it will generate new text, you know, text that didn't exist before. So if you run this, and also when you generate, you have to set up this thing called like it's kind of a surprise, you know, like a temperature. So, you know, if the temperature is too high, that means it will generate things that are very different from what the model is predicting. If the temperature is too low, then you generate things that are very close to the prediction. So you want to add some randomness in the prediction such that you know, the prediction becomes a little more interesting. This one you have to run for a while to get some results that make sense. So I put here the epoch number. So this